Okay, so maybe let's get started. So just a reminder, it's good to be reminded of these definitions, I think. So remember, the chromatic number of a graph, chi of g, is the minimum number of colors, such that g has a proper k coloring. Where we ended yesterday was with this theorem that the chromatic number is at most the maximum degree plus 1. So delta of g plus 1, delta is the maximum degree of a vertex. The degree of a vertex is the number of edges that contain it, right? And this was pretty easy to prove. We just gave a simple greedy algorithm. So not only is this upper bound true, but there's a pretty easy polynomial time algorithm which will find you a coloring using that many colors, or at most that many colors. Okay, and I just want to mention another theorem, which we're not going to prove, and then we're going to move on from there. But so one thing you could ask here is, is this, so this is always an inequality, is it ever an equality? Or when is it, for what cases, for which graphs is it an equality? And I mean, if you think about it, you can come up with some pretty simple examples where these things are equal, and it turns out that there only are a few kind of simple examples. So like I said, we're not going to prove this. It's just something which is useful to know. So there's something called Brooks's theorem so we're talking about now, what happens if this inequality is an equality. So, okay, so if G is connected, so disconnected graphs, you could always have like some components that aren't really, aren't really doing anything. But so if it's connected and the chromatic number of G is equal to delta plus 1, then either, so one of two different things can happen. So either G is a complete graph. So I don't think this is a term that I've defined yet, but it's kind of simple. So if G is a complete graph, that just means that the whole vertex set is a clique. Right, so it has all the possible edges between all the possible vertices. Or G is an odd cycle. Okay, so we talked about cycles in graphs, right? So if I'm saying G is an odd cycle, it's literally just like the whole graph is just a cycle. And it has an odd number of vertices, right? So you can see that both of these types of graphs satisfy this equality, right? So if you're an odd cycle, you have chromatic number 3, and you have maximum degree 2. And Brooks's theorem says that these are the only possible cases, right? Okay, so like I said, we're not going to prove this. This is just kind of for your interest. Yep. Yeah, which is exactly like delta plus 1. Like delta would be, the maximum degree is 2, right? Yeah, so that's exactly the point. And complete graph, it can be colored, well, you need a different color for every vertex. So if it has n vertices, you need n colors, and the max degree is n minus 1, right? Because every vertex is joined to n minus 1 other vertices. So n is exactly delta plus 1. Okay, so this is just kind of it's essentially a side note. You're not going to really, we're not going to prove it. But it connects nicely to this theorem we proved at the end of last day. Okay, so this theorem, so now we sort of understand these kind of, in some sense, trivial upper bounds on the chromatic number, that it's upper bounded by the number of, the maximum degree, or the maximum degree plus 1 in some small cases. And so now we're going to focus today mostly on lower bounds. Okay, so there's two fairly easy lower bounds that one could prove. So, but for this, I'm going to want some definitions. So I'm going to call it the clique number of a graph G. So it's denoted by omega of G, so little omega of G. And this is something this is a sort of concept we've seen before. So what is the biggest clique in the graph? So it's the maximum cardinality of S such that S is a clique in G. So the clique, remember, it's a set of vertices which are all pairwise adjacent. And the stability number well, you might be able to guess it's, okay, well, so the symbol is alpha of G, and it's going to be the max size of a stable set. So max cardinality of S such that S is a stable set in G. Stable set, remember, it's a set of vertices. It's kind of the opposite of a clique in the sense that they have no edges between them. Okay. So these are concepts we've seen before, stable sets and cliques. Now we're just saying, this is just a parameter which tells you what's the biggest size of a stable set or a clique. Okay. So one lower bound on the chromatic number, which is, I mean, it's almost too trivial to mention, but it's actually going to be a big topic of today's lecture, in the sense that we're going to, after we prove these two lower bounds, we're going to focus on the case when these things are equal, and there's some really interesting problems there. But let's just prove this kind of simple lower bound. Actually, the idea of this kind of, in some sense, it appeared kind of in the background of yesterday's lecture, because, you know, yesterday we were talking about sometimes coloring a clique, and on a clique you have to use distinct colors, right? So, okay, so to prove this, okay, let's say suppose not, right? So if it's not the case, so then there exists a proper coloring F, let's say, mapping to the colors, well, you know, using only omega of G minus 1 colors, right? Because, yeah, this is not true, then this one is strictly less than this one. But, you know, of course, by pigeonhole, okay, so, well, actually, let C be a clique of cardinality omega of G. Right? And by pigeonhole, two of them have to get the same color. So by pigeonhole, just because there are too many vertices for them to all get different colors. So there exists UV in C, U not equal to V, such that F of U equals F of V. But this is a contradiction because by definition of a clique, we know that UV is an edge, but F is supposed to be a proper coloring, right? So if you have two guys joined with an edge, they're supposed to get different colors, but here we found that they got the same color, right? But I mean, this is sort of, yeah, in some sense this is sort of trivial, right? If you take, say, 4 vertices all connected together, you can't color them with 3 colors without making 2 of them the same color, right? Okay. Okay, here's another, perhaps slightly less obvious lower bound, but nonetheless not too difficult. So the chromatic number of G is always at least the number of vertices divided by the stability number. This is again a sort of, well, you could think of it as a sort of pigeonhole thing. But okay, so let well, what's the best way to write this? Yeah. Let F be a proper K coloring of G, right, for some value of K. And I want to show that K is at least as large as this, right? And then you'll have that the minimum K for which there exists such a coloring will be at least this. So we want to prove K is at least the number of vertices in G over alpha of G. Well, here's one way to write the number of vertices of the graph, right? So you can just kind of look at all the colors and say how many vertices are there of that color, right? So, okay, so it's a proper K coloring of G. So suppose F uses the colors 1 up to K. Right, so the number of vertices then is the sum from I from 1 to K of the inverse image of the color I. So what do I mean by this? I should make this perhaps clear. I'm not sure whether everyone has seen the same sort of notation. So here I mean, the set of all vertices such that f of v is equal to I. Right, so this is a set of vertices that map to color I. Of course, every vertex maps to some color, so these sets exactly partition the vertex set. But remember what a proper coloring is, right? So proper coloring, so if you look at the vertices of a certain color, they must form a stable set because, well, that's the definition of a proper coloring. Adjacent vertices get different colors. So this is a stable set. And so this is at most K times alpha of G because the inverse image of I is stable. And now if you just divide both sides by alpha of G, you see that we've proved what we wanted. Right. Any questions about this? Okay, so, yeah. so we're mainly going to focus on this the first, well, actually both of these propositions are going to be, they're going to come into play either today or tomorrow, or today or Monday. But yeah, so yesterday we gave this kind of trivial upper bound on the chromatic number, and then, Brooks's theorem, this thing that we're not going to prove, characterizes the graphs which have equality in that trivial upper bound. So we're going to kind of focus on a similar sort of thing, except for one of these trivial lower bounds, in particular the first one involving the clique number. So we want to understand in a certain sense, graphs which have chromatic number equal to the clique number. Actually, though, it's somewhat inconvenient to look at all such graphs, but we're going to look at a certain type of graph which has this property. But it'll have a certain stronger property. So let me give a few definitions. So in some sense we want to look at, we're not just going to look at graphs that satisfy this property, but for which, so the whole graph satisfies this property, and if you take any kind of small or any kind of substructure of a certain type, it also satisfies this property. So and those are something called perfect graphs. So that's what I'm going to define. So I need a few extra other definitions, and then I can define what a perfect graph is. So given a graph G and a subset of the vertex set, so the subgraph of G induced by S is the graph with vertex set S and edge set. So the set of all edges in E. So the original graph is VE, right? Such that both U and V are in S. Okay, so you kind of take a snapshot of your graph, right? You have, say, some sort of graph. Right? And if S is the set of yellow vertices, right, then the subgraph induced by S is just, well, in this case, it's just a 4-cycle like this, right? You keep the vertices of S, and you have to keep all of the edges within it, right? So it's a if you were talking about just a general kind of subgraph, for example, I could take, these 4 vertices and just take, so this would be a subgraph on these vertices, but the induced subgraph, you have to include all of the edges within that set. Okay. But anyway, I haven't really spoken much about subgraphs in general, so perhaps that won't lead to any confusion. But and we denote the graph. So we denote this induced subgraph by G square brackets S. Okay, so G square brackets S, it's a graph with vertex set S, where the edges are the edges within S, which appear in G. Any questions about that definition? Or is it clear? Okay. Okay. It's going to be a lot of definitions today. Okay, so now I want a sort of notion of how I can say that two graphs with different vertex sets, different edge sets, are the same in a certain sense, right? And there's a natural sort of notion of isomorphism. So graphs G and H are isomorphic so when I say isomorphic, you should really think of them as being sort of, in a certain sense, they're kind of the same, right? In a certain sense, if there exists a function phi, so from the vertex set of G, which I'll denote V of G, to the vertex set of H, not just a function, well, okay, so such that phi is a bijection so it literally maps, one to one and onto, right? So it literally kind of associates each vertex of G with the vertex of H in a unique way. And so if you have a pair which makes an edge of G, so E of G is the edge set of G, so that pair is an edge of G if and only if the image of that pair is an edge of H. But basically this is just saying there's a way of kind of associating the vertices of the first graph to the second graph, which exactly preserves all the graph theory structure, right? So all of the edges of G are associated to the same kind of edges of H, and the non-edges are associated to non-edges in a kind of consistent way, right? So now I need another definition which uses both of these definitions. So say that a graph G contains an induced copy of H, or contains H as an induced subgraph. There's various different ways of saying this, but so if there exists a subset of the vertex set such that the graph induced by that set, maybe I should make it clear here. I'm talking about the vertex set of G, such that when you look at you look at that subset and you look at all the edges within it, this is isomorphic to H. So in this picture, for example, if this is the graph G, right, and if this is the graph H, then by selecting these four yellow vertices, these four yellow vertices induce a copy of H, right? So G contains H as an induced subgraph, but if I looked at this graph here, for example, just a path on 4 vertices, G contains a bunch of paths on 4 vertices, but I don't think in this, no, it does. Okay, I was going to say it doesn't contain an induced one, but it actually does. So, right, so this graph also contains this one as an induced subgraph by looking at these 4 vertices, right? So that gives you an induced 4 vertex path. Okay, so now we can finally define this notion of perfect graph. So graph G is perfect if okay, actually I technically don't need these last 2 definitions, but I will later. So I'm going to write this in a different way than I planned to. So I'm just going to write that the chromatic number of the subgraph induced by S is equal to the clique number of the subgraph induced by S for all subsets of the vertex set. Right. So in particular, if I just take S to be the whole vertex set, the subgraph induced by that set is obviously just the whole graph. So in particular, G has chromatic number equal to clique number, but if you kind of zoom in on any substructure in G, it also has the property. Right? So in some sense, this is, yeah. So we're kind of addressing this, when is this upper bound, or so this lower bound there tight, but we want a sort of stronger condition that it's tight for all the induced subgraphs. Okay. It turns out we've actually seen some graphs like this somewhat in disguise. Okay, so yeah, so the so here's a so example. So let G be a bipartite graph. So this is going to be an example of, it's not just a single example, but an example of a big class of perfect graphs. Okay, and let now, so H be, so here I was talking about H being an induced subgraph and stuff. This H is going to be different, but so let H be a graph with vertex set E, so the graph is VE, right? Where if I take 2 elements of E, so they are adjacent, meaning they're joined with an edge in H, if and only if they are disjoint. Okay. So you take, so the vertices of H correspond to edges of G. When 2 edges are disjoint, they're joined in H. Right? This is technically, this turns out to be the complement of the so-called line graph of G. Okay, I don't think you technically need to know this terminology of line graph yet, but when we use it, we'll need it. Well, I'll give you the definition. We've seen a sort of definition in terms of digraphs for line graphs, but anyway, so this is But anyway, so you can just kind of understand this definition of H. And it turns out that H, any such H that you get in this way, gives you a perfect graph. So any questions about the definition, or is it okay? Okay, and this is something you might not realize it, but you've seen this before. Okay. So this is going to be simply the same thing as Koenig's theorem. Remember Koenig's theorem, it says that the biggest size of the biggest matching in a bipartite graph equals the minimum size of a vertex cover. Okay, so to see how you can derive this from Koenig's theorem, so first, you can ask yourself the following question. So what is a clique in H? Right, so it's a set of edges of G which are pairwise disjoint. Right, because if it makes a clique in H, so that's a set of vertices that are all joined together, then any pair of those edges in G must be disjoint. But what's a pair of, or a set of disjoint edges? It's a matching, right? Right, so therefore, if you take the biggest clique in H, that corresponds to the biggest matching in G. So omega of H is nothing more than nu of G, where you might remember, so this is the notation to mean the cardinality of the biggest matching. Okay. And now we have to think of, so what is a stable set in H? Well, it's kind of, it's the opposite of clique. So it's a bunch of edges of G which pairwise intersect. So which pairwise intersect. Right, but if you think about it, so if you have a bunch of edges, so in a bipartite graph, if you have a bunch of edges which intersect, they all have to intersect the same vertex, right? Because if I have, for example, I have this edge intersecting this one, right? If I want to add a third edge which intersects both of them, well, one way you would try to do that is maybe make the edge go between here, but that obviously, in a bipartite graph, that's not possible. This would make an odd cycle. So the only way to have another edge intersecting both of them is to make it use the same vertex. So the stable sets all look like this. Stable sets of H are sets of edges in G which share a vertex. And it might be on either side of the bipartite graph. Right? But, okay, so now let's, so we want to show that the chromatic number of H is equal to the clique number. Well, technically I need to show this for every induced subgraph, but every induced subgraph will have the same sort of structure. It'll be a complement of a line graph of a bipartite graph. So now we know what a stable set is in H. We can say what's a proper coloring of H. So given a proper coloring, F of H using colors, let's say 1 up to, say, K, right? So we know that each, if you have a set of vertices that all get the same color, that forms a stable set, which gives you a set of edges in G that all share some vertex. So for each I, so for each color, let VI be a vertex of G such that every edge of G which has color I contains VI. Okay, and we can do this because as we've pointed out, if you have a stable set in H, that corresponds to a bunch of edges that all share some vertex, and we're just letting VI be that vertex. So then, V1 up to VK is a vertex cover of G, right? And that tells you that tau of G, so this is the size of the smallest vertex cover, is at most the chromatic number of H. Right? Because for every coloring with K colors, I found a vertex cover which has at most that many, well, it has exactly that many elements. So the smallest vertex cover must have at most the chromatic number of elements. And so if you want to prove the other direction, it's also not hard. So if you have any vertex cover, you can turn that into a coloring of H. So, and if V1 up to VK is a vertex cover of G, then just let F be any function from the edges of G to 1 up to K, which maps any edge in the graph to one of the vertices VI contained in it. Contained in E. Right, it's a vertex cover, so every edge has such a vertex contained in it. And if we just do this kind of in an arbitrary way, so some edges might have just one of these vertices in it, some might have two, but we just pick kind of arbitrarily. And this gives a proper K coloring of G, of H. And that proves that then chi of H is at most tau of G, and so they're equal. Now the kind of final thing is that, so now we know chi of H equals tau of G, which by Koenig's theorem is equal to nu of G, which we proved before is equal to omega of H. Right. And okay, I was also claiming that it's perfect, so you need to have this condition for every induced subgraph, but it's not hard to see that an induced subgraph of H is the same thing as just taking, it's again has this property that it's constructed in the same way from a subset of the edges of G, right? Okay, but anyway, so this is, so there's this nice connection between, this bipartite matching and vertex cover thing and perfect graphs. And actually, one nice thing about perfect graphs is that it actually unifies a lot of different concepts which existed throughout combinatorics and combinatorial optimization. So like we've just seen, it kind of encapsulates this bipartite matching, Koenig's theorem, but it also includes a lot of other things which are beyond the scope of this module, but I included them in the notes, so if you're interested in further reading, there's some examples there. Yeah, another thing, so basically I'm going to end the lecture with kind of setting up what we're going to do next Monday. But before I do that, let me just say that so there was some other motivation, which I'm not going to go through in detail, but the kind of historically perfect graphs. So I think perfect graphs are interesting, because first of all they have this condition that the chromatic number equals the clique number, but that's not why they were actually studied first. So perfect graphs are motivated by applications in information theory, so there's some kind of applications to sending messages through a noisy channel. Right? So this is again something I'm not going to have time to discuss more about in the lecture, but there's some discussion of it in the notes. It's not examinable, but it's there for your interest. But there is some actual, well, at least in the beginning, they were introduced for some actual reasons. There's applications, to basically kind of making code words and sending things through a noisy channel. Okay, so one thing I haven't addressed, so I've given you a definition of perfect graph, but I haven't really addressed what really are they? So what is the structure of perfect graphs? And that's something that people actually for a long time, there's some some old conjectures which were around for quite a while, and it took people long time to understand really what are perfect graphs. So two conjectures which are now both theorems. So one was called the weak perfect graph conjecture. So both of these conjectures are due to Burge, who is the person who introduced them. And it's that if G is perfect, then the complement of G is perfect. Right? Remember the complement, you have the same vertex set, and the edge set is all the pairs. You kind of flip the edges, like a non-edge becomes an edge becomes a non-edge. And this is actually what we're going to prove on Monday. So this was proved by Lovász in 1972. I think these conjectures date back to 1965. So now this is actually a theorem. Okay, it still doesn't really tell you a lot of information about the structure. So that was the strong perfect graph conjecture. Again, due to Burge, I believe it was 1965, that G is perfect if and only if G does not contain an induced copy, of an odd cycle I'll kind of state this way. So nor does the complement of G, meaning the complement of G also does not contain an induced copy of an odd cycle. Okay, so this sort of gives you I think this is a really nice structural characterization of these graphs. And this was open up until 2006. So the strong perfect graph conjecture was proved in 2006 by Chudnovsky. So this is kind of just to give you some background. It's not crucial that you know these things, but Chudnovsky, I should say Robertson, Seymour, and Thomas. And so now this is not just a conjecture, but it's actually a theorem. And this is way too complicated for us to possibly present in this module, this strong perfect graph theorem. But the weak perfect graph theorem is somewhat nicer, and that's what we're going to do on Monday. Any questions before we stop? Okay, so see you on Monday.